Hello. So in this video, we're going to talk about Haberman's section 1.5, where the focus is deriving the heat equation in higher dimensions. And so kind of our development will be essentially, it's essentially the same derivation as in one dimension. It's just the question is, right, how things behave in higher dimensions. But then, so this bit, all of this is going to be essentially same as 1D, where we'll set up a conservation law. We'll say, well, here's what the total energy for this 2 or 3 dimensional region is. Here's how it changes in time in terms of kind of where energy is going to flow and how we're going to gain or lose energy. And then we're going to put things together using Fourier's law to describe flux in terms of temperature, and then get kind of a similar expression as we had before, but now that's valid for higher dimensions. After we have that set up, what we're going to do is kind of look at some of the other pieces that we've been discussing relevant to actually solving and kind of understanding solutions to PDEs. In particular, what we'll do is we'll talk about kind of what initial and boundary conditions look like in higher dimensions. We'll talk a little about kind of what these equilibrium solutions might look like and how we might start computing them and kind of what those equations look like. And then finally, we'll talk about what the heat equation looks like in different coordinate systems. Yeah, okay, so let's get started. So in one dimension, right, the kind of version of the heat equation that we derive looks like this, where C is specific heat, rho is the mass density of kind of your material. You have one time derivative here, you have one spatial derivative here, and then this term right here was phi, or the flux. Fourier's law lets us write in this way, where this tells us something about how heat can flow, or how energy can flow in a material, and then another spatial derivative, gradient, plus some black box kind of a source term for anything else that can happen in the system. And so then the question is, well, right, what do these pieces look like in higher dimensions? So in higher dimensions, now here, x, this might be the vector x, y, z, or just a 2-dimensional thing. It doesn't really matter, but the point is that now specific heat and mass density are now a function of multiple variables, right? So you're plugging in a vector, you're getting back a quantity, but we still have specific heat, mass density, one time derivative of u, where except now the solution u that we're looking for depends on both space, kind of this higher dimensional space and time. On the other side, we still have this black box source term for anything else, but now these spatial derivatives, instead of just being d dx, right, we have a little more room to kind of take derivatives. And so the corresponding operators are now this divergence operator and this gradient. Okay. Otherwise, we still have this function k0 of x, which tells us how the material lets things or tells us how much the material lets things flow through it. We're here, recall that divergence. Let me write, so if you have a vector, say v1, v2, I'll just write in 2 dimensions, then the divergence of this vector is going to be derivative in the first coordinate of the first component of the vector plus the derivative of the second component of vector in the second direction. And then if this was like a 3-dimensional vector, then you'd also add, say, d v3 dz. But so that's this divergence operator. And then of course the gradient. This is going to give us the vector du dx and then du dy, right? Just take the function you want, take the partial derivatives in each direction, and then keep track of those as a vector, okay? But this is going to be our goal, kind of our first goal in this section. And so the point here is, right, we see a lot of the same pieces. That's pretty much the same. This is the same. And then we have these derivatives that match up, these derivatives that match up. But otherwise, it's essentially the same expression. Okay. So let's see where this comes from. Okay. So what we're going to do is essentially the same derivation, as I said. And so the setup is going to be, well, for some region R, where for us, just going to imagine like a three-dimensional blob. So something like that. And then the question is, right, if you pick any point in here, how does the temperature near that point change in time? Okay. So this would be R in like a region in 3D. Of course, you can also have a region in 2D, and that's just going to look like something like this, say. But so how we're going to go about this is the same way we did in one dimension. What we're going to do is we're going to consider kind of how the total amount of heat energy or thermal energy, we're going to look at how that changes in time. And we're going to express that change in terms of, one, how much heat energy is flowing across the boundary or flux across the boundary, plus anything else that can happen. Okay. So this is going to be our source term. This is going to be a ddt of kind of that total heat energy. And so the thing that's going to take a little more work to write out correctly is going to be this term right here. And part of that is because in one dimension, right, we only had really one direction that energy could flow, say left or right. But in 2 or 3 or higher dimensions, right, you have a lot of possibilities. So a lot of the work will be coming up with the right things to write down and the right way to express things. Once we've done that, though, recovering the heat equation isn't too much extra effort. Okay, so let's start with this first one. How does heat energy change? So to do that, we first need to figure out, right, what is the total amount of thermal energy in the system? And so here, what we're going to do is we're going to say, well, right, so suppose this is our three-dimensional region, okay? We're going to have 3 functions associated to kind of points in this region. First function is going to be a specific heat, right? And so recall that the specific heat near a point or at a point X tells us how much energy we need to add into the system kind of at that point to raise the temperature by 1 degree. And this is going to be per mass. To convert this whole thing to something per volume, we need to incorporate kind of a mass density, which tells us, right, how much mass there is per unit volume for our region or blob. If we want to raise the stuff to a certain temperature, well, multiply specific heat times mass density times the temperature. That's going to give us energy per volume. And so then finally, we need to multiply a volume element, right? And then that'll give us energy. And then we can add that up or integrate it to get the total energy in kind of entire region, right? So maybe one way to think of this is, right, so let me write it over here. So C rho U, and of course, this is a function of both space and time. This is going to be, right, joules, or have units, joules per volume. So if we want to know how much energy is in this little infinitesimal box here, that's delta X, maybe delta Y, delta Z. Then C rho U times the volume of this box, which in this case is delta X, delta Y, delta Z, right? we have energy per volume times volume. So this is going to be joules, right? And then what we do is, well, take a bunch of these boxes, add them up. That's going to give us this integral over the entire region R. Okay, so this, right, just compute the total energy for each infinitesimal box, add up all the boxes, let the boxes shrink to 0. You're going to get this integral. Okay, point is, this is our expression for the total heat energy in this region R. And so, of course, later on, what we're going to do is, well, take a time derivative of this and then relate it to some other quantities, but we'll get there. Okay, so this is the total energy. Great. Now let's talk about how heat energy is going to flow. Okay, so in one dimension, right, when we were talking about how things flowed, we could just specify a direction that it was flowing, right, left or right, and then the that would come in the sign of kind of the flux, right, and then the absolute value or the magnitude of the flux, that was just how much stuff was flowing. Okay, but in one dimension, right, direction, we only need to specify a sign, right, whether it was going left or negative or right for a positive sign. Okay, in higher dimensions, right, you have a lot more directions you can flow. So to specify direction, we're going to specify a vector, right? And so in higher dimensions, right, how we work with flux is we'll generally visualize flux as some sort of vector field, right? So when I'm drawing here, these are all really, really small arrows. The idea is that, well, how is energy flowing? It's flowing sort of like this. Okay. Down around here, energy is flowing not very fast, or not a lot of energy is flowing. But as soon as you kind of get through this point right here, then all of a sudden you're going to have a lot of energy flowing. Okay. And so the point is, right, we're describing kind of the flow of this quantity by these vectors, which have both direction and magnitude. Okay. And so one other point I kind of want to highlight is, right, this vector field, we're associating a vector to each point kind of in this region, right? So in this case, you can think of this as kind of a two-dimensional, right, in a plane, this vector field in the plane. And so if you pick any point, maybe you pick a point out here, I'll be able to tell you what vector is associated with this point, right? So maybe if you pick a point over here, maybe that'll be the vector, okay? And so we've just sketched a few of these, but the point is you pick any point in this region, you'll have this vector phi that's telling you how much stuff is flowing, say, at that time, at that point. Okay. Okay. And so one other piece I want to highlight is, right, for a region, we're also going to have these normal vectors that we're associating to the boundary, say, of that region. So what does that look like? So I'll draw a two-dimensional picture here, and then we'll revisit some of this in the next slide. And so this in here, the interior, this is the region R. Okay. And when we talk about boundary, right, we're talking about exactly this collection of points. It's kind of shaky, but that collection of points right there, that on one side, you have points within the region R. On the other side, you have points that are not in the region R. Okay, so the boundary of a region is kind of what you'd intuitively think of it as. But then the point is that at every point of the boundary, we have this kind of normal vector and we're going to pick a convention so that this normal vector always points out of the region. And so drawing this picture, these normal vectors are going to look like this. So this would be the normal vector at this point right here. And we're going to normalize these normal vectors so that they all have kind of unit norm or unit Euclidean norm. But if you walk along the boundary, every point you pick, right, there's going to be a normal vector that points outwards. And so you might ask, well, what if the boundary isn't very well behaved, and like you have cusps or other kind of corners or other weird things? That can happen, and we're not going to worry about that in this course. But there are ways of dealing with them, and in practice, those cusps don't actually really matter that much. But again, we're not really going to worry about those special cases or those cases in this course. Okay. Okay. So how do we put this together and compute just how much flux there is over the boundary of a region? So, so before that, I want to talk about sign convention as well. So these two lines are the same as on the last slide. And actually, let me copy this picture. Nope. Okay. Put up a little bit. Okay, so the point is that, right, if we want to know how much just the amount of flux that's flowing in a direction n, the way we compute that is using kind of this inner product or this dot product phi dotted with n, right? And so of course, written out. So in this two-dimensional case, phi might be a vector with two components. So, right, plug in a point. Phi sub 1 is going to tell you the x component of that vector. Phi sub 2 is going to tell you the y component of that vector. But if phi is that, and then n is kind of the vector with components n1, n2, then this quantity phi dotted with n is just going to be phi 1 times n1 plus phi 2 times n2. Okay. And so what this quantity is telling us is that, well, this is sort of essentially projecting the vector phi onto the vector n, and then recording just kind of the magnitude of that projection. Okay, so if we have a vector field of flux that's kind of maybe going through here, something like that. Let me draw one more. Another one. Okay. So say this is our vector field phi, and then we have these unit normals. Question is, right, pick a point, say for example here, right? How much of phi is flowing in the direction n? Right, well, looking at what we drew, this vector is kind of on top of this vector, right? So, right, the flux through this point is essentially the magnitude of this vector. Okay? And that we quantify, or we actually compute via this thing right here. Okay? On the other hand, right, over here, sure, we have this vector phi that's coming in here. And so maybe closer to this point, what is the actual vector? Maybe it's something like that, right? If we want to know how much stuff is flowing over the boundary at this point, right? Well, we can compute it in the same way. Take the inner product of the vector at that point, dotted with the normal vector at that point, okay? But the observation here is that this vector, phi, is pointing in the opposite direction of this vector, this normal vector, n, right? So at least this point, kind of the takeaway would be, well, they're pointing in opposite directions. So stuff is entering here, or it's kind of going against the direction of the normal vector. And what we can take away is that, well, what is a sign of all of the stuff? If phi and n point in the same direction, you'd maybe say if the vectors are more or less on top of each other or generally pointing in the same direction, this projection or this inner product is going to be positive, right? And then the takeaway is that, well, phi and the normal vector are pointing in the same direction. Whereas if it's kind of flipped and phi and n are pointing in opposite directions, right, then we get the opposite of this. And in fact, this inner product would be negative, right? So looking at this, right, especially kind of around here-ish, if you compute phi dot n, all around here, phi dot n will be roughly positive. Around here, phi dot n will be negative. And then probably like here and here, phi dot n will probably be about 0, just because these normal vectors are pointing like that, and then phi is pointing like that. So phi and n are going to be roughly orthogonal, but anyways. Okay, so that's how we're going to work with kind of the flux and kind of the boundary of a region we might be interested in. The main things we're going to be doing are computing kind of the amount of flux that's crossing over the boundary. And that we're going to get via these dot products, phi dotted with n. And then the other thing to keep in mind is that the sign, right, if phi and n are pointing in the same direction, sign of this dot product will be positive. They're pointing in opposite directions, it'll be negative. If phi and n are orthogonal to one another, this will generally be 0, will be 0, but yeah, okay. So how do we put this together and actually kind of incorporate it into this conservation law and computing, right, how energy changes in time? Okay, so rate of change of heat energy, right, that was an expression before. Sum up all of the infinitesimal boxes in the region R that you care about. What are we summing up? Well, the energy for each of those boxes, which is going to be C, rho, U, dV. Okay. We're also going to kind of introduce the same notation for this source term. So this term down here, the heat energy generated inside per unit time. This was this expression Q of X T, in this case dV. Okay. Right, so but now, right, the question is, well, what was the heat energy flowing across the boundary per unit time? Okay. So the amount of flux, right, kind of the flux, the magnitude of that flux, that was this expression phi dotted with n, right? Right, because pick a point, how much stuff is flowing right across the boundary at that point. Well, take the vector, see how much of it is pointing along n, along that unit normal. So that was phi dot n. Okay, so that's the quantity that we want to kind of add up all along the boundary. So if kind of this notation here, I have a 3-dimensional region R, right? The boundary for a 3-dimensional region is going to be a 2-dimensional thing. So we're going to be adding up a bunch of things for this 2-dimensional boundary piece, which we've been calling B. Okay, and then I'll have a ds. So this just means, right, here's a function we want to integrate. We want to integrate over a 2-dimensional thing. So we're going to integrate with respect to surface area. Okay. Okay. So this is just adding everything up, but now we also need to kind of keep in mind the signs. So let's take a look. So question is, when this term is positive, right, do we want that adding to or taking away from kind of the total energy, right? Because we're interested in the rate of change of heat energy. Okay, so let's take a look. So going back here, so kind of along this portion of the boundary, right, the vector field we drew is more or less pointing in the same direction as these unit normal vectors. So all along here, this dot product phi dot n, that's going to be positive. Okay. If we're interested though in how the total amount of energy is changing, well, in this region here, we have a bunch of energy. Over here, phi dot n is going to be positive, right? But phi dot n is telling us how much energy is flowing across the boundary, right? So all the energy that's flowing across the boundary here, right, is going to be taking away from the total energy already in here, say, right? Or in other words, energy in here is leaving across this boundary, okay? The dot products along here were all positive. So whatever term we're getting, or right, once we add up the contribution of the dot products over here, then we should subtract them from the total energy. So writing that out, so over here, we should have a minus integral over the boundary of the region of phi dotted with n. We can also check that with portions where energy is entering the region, right? So along here, the vector field that's been drawn, right? These vectors are pointing in. So kind of along here, right? Energy is entering this region. Okay. All along here, phi dotted with n is going to be negative. Okay. But, right, energy that's crossing into the region over here, that's adding to the total energy, right? So if we want a positive contribution from all the stuff over here, and kind of the magnitude of what we're computing over here is all negative, then we need to hit that with a negative sign so that we do in fact get the positive contribution that we would intuit from the fact that this vector field is pointing in here. Okay. Yeah, and so technically, so let's see. So technically this term here, this is missing a ddt, right? Because we're looking at the rate of change of heat energy. But otherwise, these are all the pieces that we're going to work with, right? We have, right, total energy, how it's changing in time. And the claim is that, well, the change of the rate of change of heat energy, that's going to be what we gain or lose across the boundaries via this flux vector field. And we're quantifying, right, what we're gaining or losing over the boundaries, we're quantifying in this way. Plus, we have whatever else is happening to the system, and that's just this, right, q of x comma t, the integral of this source term. Okay. Okay, so, right, putting that all back together, kind of ignoring some of these arguments, the conservation of heat energy, and here I'll sketch kind of what this looks like in 3D. So this is going to be a region R, and then the boundary is going to be what you have up here, together with kind of these pieces, whatever. Right, so the B, the boundary is just the shell, R is the shell in the interior. Change in heat energy is going to be, right, the total contribution of, right, the flux across the boundary plus the source term. Okay. Cool. So what we want to do now is, right, well, you could say three things. So first thing, move this ddt in here. It's not too bad. Second thing, right, here we have integrals over the entire region R in the interior of this thing. Here we have, right, an integral over the region R. But over here, we have an integral over the boundary. So one thing we want to do is convert this integral over the boundary into, right, an integral over the interior. And that's something that we'll be able to do, right? So kind of the translation from this to this is essentially kind of what we did with the fundamental theorem of calculus. We will be able to do that using something called the divergence theorem. So that's one thing we want to do. The other thing we want to do is write this in terms of temperature, and that'll come via Fourier's law. Okay, so to get this in terms of, or to rewrite this integral as an integral over the interior, right, we're going to use this thing called the divergence theorem, which says if you have a vector field A, so in this case, A, we'd write as a vector A1, A2, A3. And the normal vector to our region R, N1, N2, and 3. Okay. So this here is essentially what we have in this conservation law so far. And the claim is that, well, if you want to compute, right, this vector field dotted with this normal vector over kind of the boundary of your region, that's equivalent to computing the divergence of your vector field over the interior. Right, so here, right, divergence of A was dA1 dx plus dA2 dy plus dA3 dz. A dotted with n. This was A1 n1 plus A2 n2 plus A3 n3. So I won't go through the proofs here, right? But essentially, the idea is the divergence of a vector field is measuring something about, right, how much that vector field flows through a point. Okay, so if you want to compute, right, kind of what this divergence is, kind of for an entire region, well, it turns out that, you know, so if you have two nearby points, what is flowing into this point, let's say it, what is flowing into this point is essentially what kind of flowed out of the point right next to it. So those contributions are going to cancel. And then in the end, the only contributions to, right, how things are flowing, you're just going to get them over the boundary of the region. Of course, it's not complete proof, but that's more or less the idea of maybe why we'd expect a result like this, right? Okay. But for our purposes, right, the things that we were working with, and so I can write it here. So for us, let me move this down. Pull this off. Right, so for us, we were computing minus the integral over b of our flux dotted with the normal vector, integrate over the surface. The divergence theorem tells us that this integral is equal to minus triple integral over the interior of the region of the divergence of the flux. And so one other point, right? So all of this is stated as if the vector fields and the normal vectors, whatever, were all three-dimensional things. Same exact statement holds for two-dimensional regions, right? So if you have like a region in the plane and the boundary is a curve, it also holds for one-dimensional regions, right? Where the region is going to be like a line segment and then the boundary is just going to be 2 points. And so the one-dimensional version is pretty much just the fundamental theorem of calculus. But I digress. Okay, so this is what we really need in our derivation. Okay, so right, this was written 2 slides ago, right? Rate of change of the heat energy, flux across the boundary, and then this black box source term. Divergence theorem tells us that this is equal to this. Okay. And so then finally, right, so we're going to move this derivative in there so that we get partial derivative u with respect to t. But then what we're going to do is, right, move all of these integrals to one side. Okay. So the intermediate step is, of course, so I'll write it here. So triple integral c rho du dt dv plus triple integral of divergence of phi dv minus triple integral of q dv, all of this equal to 0, right? But we have same integral, same bounds, right? Same integral, same bounds, same integral, whatever. So we can combine all 3 of these integrals into one integral. That gives us integral of c rho du dt plus divergence of phi minus q. With respect to v, that's all 0. Right, and then this is what's written right there. Okay. Great. So what next? Well, kind of how we set this up is, right, sure, we said there's some region R, it has some nice enough boundary B. For that region R, this equation holds. This is how kind of temperature evolves for that region. But, right, we didn't specify what R was. So there's a lot of freedom. R could be a massive blob. R could be, right, a tiny, I guess, filled in sphere around a point. Okay. And so the claim is that, right, this integral holds for any possible region we'd want. So if this integral is 0 for every possible region, then kind of the integrand, or the function that we're integrating, right, this function right here, this function must be 0. Okay. And so that gives us kind of the first form of the heat equation, which is c rho du dt plus the divergence of the flux minus q is equal to 0. Right, which is almost what we want. The only thing we need to do now is convert phi into an expression in terms of temperature u. Yeah, so this is almost there. Just one more translation, and then we'll have this higher dimensional heat equation written out or derived. Okay. And so just as in the one-dimensional case, in higher dimensions, we have Fourier's law, which tells us how kind of the flux of energy relates to the temperature, particularly the gradient of the temperature. And so the observations are all the same, right? If the temperature is constant, no energy flows, okay? Or you might say, right, the gradient of the energy is 0, or I guess the flux, but the gradient of the temperature is 0. If there are temperature differences, heat's going to flow from the hotter region to the colder region. The greater the temperature difference, right, or the greater kind of the magnitude of the gradient of the temperature difference or the temperature. So the greater the temperature difference, the greater the flow of energy. And then of course, you know, different materials, different amounts of energy that's going to flow, even with the same gradient. Okay. So all these observations put together give us the exact same quantity here. So kind of, as we've been saying, right, in higher dimensions, right, this gradient or kind of these differences, you know, they're a little more involved. There's a little more freedom in which way kind of these differences point, say. So kind of this change in temperature now is kind of the gradient of the temperature, which is now this vector grad u. As before, kind of just these flow properties of material we're encoding as k0 of x. But with all these together, right, flux is going to be proportional to, right, some property of the material that tells you how things can flow times the gradient, right, which encodes direction and magnitude of temperature differences. And this minus sign, right, comes back to things are flowing from hotter to colder, right? Right, and so maybe another way to intuit that is, right, so in general, the gradient of a function, that's going to point in the direction of greatest increase of the function value. Right, but if your temperature is increasing, you don't want flux to point in that direction. You want flux to point in the opposite direction, right? You want things to flow kind of away from, you know, maxima. So this is pointing in the direction of greatest increase. Throw in this minus sign here. Now it's going to point away from the hotter regions, but otherwise, right, Fourier's law is essentially kind of the same sort of expression. Okay, so this tells us how the flux of energy relates to the temperature. So plugging this expression back into the heat equation we just derived, we get the following, right? So this is what we derived from this conservation law, right? By looking at for some arbitrary region R, right? What is the change in energy? It depends on, right? So du dt depends on the divergence of the flux. So then the question is, well, how does divergence of the flux, or how does flux behave with respect to temperature in higher dimensions? So plugging in phi is equal to minus k0 grad or gradient of u. Copy, so phi, this was minus k0 gradient of u. This goes in there. So this minus sign comes out front and gives us that. Otherwise, k0 grad u is going in phi, so it gives us that. So this is the expression here with just phi plugged in, and now moving all of this to the other side, right? Signs flip, and we end up with this expression. Okay. So the heat equation in higher dimensions, right? The only changes are the two spatial derivatives on the right-hand side. The outer one is replaced by the divergence operator. And then the inner spatial derivative, that's replaced with just this gradient operator. Okay. So we can write this. There are a few different ways we can write this. So assuming that C rho and K0 are all constants, and there's no source term, what we get is, right, so divide by C rho over there. So little k is k0 over C rho, you get that. and we can pull it out from there. But then otherwise, we're left with the divergence of the gradient. Okay, so this expression right here, right, divergence of the gradient, pops up enough, special enough that often we're going to call it, so these are equal. This operator we'll call like nabla squared, in a sense, because we're kind of applying this nabla thing twice. Right, but what is this nabla squared? Written out is just this expression. Okay, so when all of our thermal properties are constant, we rearrange things. The heat equation tells us, well, how does heat evolve in time? Take all the second spatial derivatives, sum them up. Right, the time evolution of temperature is going to be proportional to this sum of second spatial derivatives. And right, why is this the case? Well, I mean, if you just kind of write out what the gradient of u is and then take the divergence of that, right, you're going to get something like, so in 2 dimensions, you're going to get du dx in the first component, du dy in the second component. Now you take the divergence of that, right, apply a ddx to the first component, ddy to the second component. You're getting exactly d squared u dx squared plus d squared u dy squared. Okay. But anyways, so right, this operator of nabla squared shows up enough, it's important enough. We usually call this the Laplacian. Sometimes it's denoted just by an L. Sometimes it's denoted by a delta. We are going to avoid both of these notations. This one, just because I guess you kind of could use it. Doesn't really matter. But we're mainly going to avoid this because, right, for some of these derivations, we've been using this to denote like a small increment. And we're going to try to avoid overloading that notation. Okay. But the point is that here, this operator, delta or nabla squared u, which gives us this thing right here, this thing is called the Laplacian. Okay. But otherwise, yeah, this is a 3-dimensional heat equation, at least when things are constant and we have no source. Okay. And so kind of what I was getting at a second ago, right? In 2 dimensions, right? This is the expression that we get. The 2-dimensional version of this, we also call the Laplacian. But yeah, we have essentially the same expression, and part of this is because the divergence theorem also holds in kind of going for a 2-dimensional region with a 1-dimensional boundary. The divergence theorem also holds there. So all the steps that we were doing to derive this, mainly, let's see, all of this stuff, right? If these are 2-dimensional integrals and this is a 1-dimensional integral, all of the same steps hold. So then this also holds for 2-dimensional regions. But anyways, cool. So that's the heat equation in higher dimensions. Okay. So one of the observations that we've had for the 1-dimensional heat equation is that, right, specifying the partial differential equation isn't enough to uniquely solve, right, kind of a problem. You also need to specify something about how kind of the system started, right, what the initial temperature distribution was. And you also need to specify something about what's happening on the boundary. Okay. Right, different boundary conditions will get you different solutions. Okay. So what do those look like in higher dimensions? So for the boundary conditions, right, same thing as before. We can specify something about the flux. We can specify something about just the temperature. But the point is that, right, so in the two-dimensional case, say if this is our region R, to specify a boundary condition means that for all of these green points, we need to say something about what the temperature is. And so this equality here, u of x comma t is equal to t of x comma t. The understanding here is that this function t of x comma t, this is given, right? We're specified a temperature at the boundary. And whatever temperature we're looking for, right, has to equal that. But this equality just holds for these green points. Okay? And then generally the question is, right, well, what is the temperature inside? Okay. But yeah, so this equality should be understood as just holding for these green points on the boundary. So that's one kind of boundary condition, but that's enough to get us started here, right? The other piece we need are initial conditions, right? What the initial temperature distribution was. So in higher dimensions, right? So if this is a region R, what that might look like is just, right, at temperature or at time 0, time t equals 0, we might say, well, maybe this is a graph of, the initial temperature distribution. Okay, maybe it's something like Gaussian, but otherwise, in here, temperature is higher. Out here, temperature is smaller, possibly. So that might be one kind of, or one initial condition. Another possibility might be, I don't know, maybe it's something almost bimodal. So a lot of temperature here, or higher temperature here, less temperature kind of here, and then possibly 0 temperature up there. But the point is, right, we still need to specify at time 0, here's what the initial temperature was. It's just now these are functions of more than one variable. Okay. Cool. Right, so specifying the temperature, right, as a boundary condition isn't the only possibility. Just as in the one-dimensional case, maybe our region is insulated, right, so that there's no flux across the boundary. We can use that as a boundary condition as well. And so what that looks like here is, right, well, recall that this was the flux, and so technically this, so writing up the arguments, k0 of x, grad u evaluated at x comma t. For this boundary condition, we want this to hold for all x on the boundary. And so another picture, if this is R, this is our boundary B. We want this to hold for all x on the boundary B. But that's another viable boundary condition, right? When we solve for temperature U, the requirement is that, well, whatever the temperature, whatever the solution function is, if we compute the gradient and evaluate it along the boundary, that gradient should be 0. Okay. Of course, you can have other possibilities. So one other possibility is something like Newton's law of cooling, where now you're specifying something about the flux as well as the temperature. And you're saying, well, some combination of flux and temperature, here's an equation that those have to satisfy for every point along the boundary. Yeah. Okay, but those are just some examples of boundary conditions that can and do arise. But the general methodology is the same, right? We have a PDE, we have an initial condition, we have boundary conditions. Those are enough to, uniquely say, sure, here's how temperature evolves through time. Okay. So the thing is, right, solving the heat equation in higher dimensions, I mean, it's doable. It's just harder and not necessarily something we want to do by hand, just because there's a lot more that's involved. But stuff we can kind of do by hand are kind of solving these equilibrium solutions, okay, especially using some of the tools that we'll develop in this course. Right, so recall, right, what's an equilibrium solution? Well, these are solutions that don't depend on time, okay? And so in particular, right, du dt should be 0. Generally, these arise if you let the system kind of evolve for a really, really long time. And then you ask, well, what happens, after a while? A lot of times, kind of your temperature distribution will converge to some sort of equilibrium solution. Yeah, and then what will happen is, right, time derivative is 0. But computationally, this is the condition we impose, right? So if we plug this condition into the heat equation, right, and not necessarily say anything about C rho, I guess we're saying something about K0, but possibly we have a source term as well, then plug this in, you get this expression, okay? If K0 is constant, this can get pulled out, move Q to the other side, divide by K0, you're going to get this equation here, right? And so written out, say in 2 dimensions, this, recall, is d squared u dx squared plus d squared u dy squared. And if it's in 3 dimensions, you have a plus d squared u dz squared. Okay. But the point is, if we're looking for equilibrium solutions, this is the equation that we're led to. Okay. So these show up enough. Usually they're called Poisson equations, or a Poisson equation, or Poisson's equation, whatever. But the point is that you have some function that's specified. Okay. And then the question is, which function u? So if you take kind of these if you apply the Laplacian to this mystery function u, you get this prescribed function over here. Okay. So those are equations that show up in many situations. As a special case, right, if we want 0 source term, right, so if this becomes 0, then we end up with something that we'll often just call Laplace's equation, or a Laplace equation, and it looks like this. Yeah, and so we'll look at solving these equations for some relatively simple geometries in a bit, but these are things that can arise. Okay, so all of this stuff is kind of a repeat of what happened, right, in the one-dimensional setting, just, right, translated into a 2 or 3-dimensional or higher dimensional setting. Okay. So the last thing that I want to mention is, right, well, what happens if kind of you want to solve some of this stuff with respect to different coordinate systems, okay, which isn't something that we really see in one dimension, right? So what we're going to do briefly is say a little about kind of what these problems look like if you change your coordinate system. Okay. So, right, this Laplacian kind of that we've been writing previously looks like this. Okay. And so generally, right, when you apply this to a function, say u, you interpret this as saying, well, take 2 derivatives in the x direction, 2 derivatives in the y direction, 2 derivatives in the z direction, add them up. Okay. Great. But sometimes we don't want to work with Euclidean coordinates, right? Sometimes we want to work instead with like polar coordinates, okay, where I guess in 3 dimensions, these might be called cylindrical coordinates, but at least the 2-dimensional piece, right, if that's x and y, what we're doing is we're saying kind of a point there. It's associated with an angle. And I'll do it like this, and a radius r, right? So, right, two ways to specify points in a plane. And so the question is, well, right, what do these second spatial derivatives look like if we're using r and theta as our coordinate system? Okay. So the punchline is that in polar coordinates, what does the Laplacian look like? Well, it looks like this. And so technically, there should be a u right here because this operator is already applied to u. And I think the same down here, Nabla squared u. Okay. But the point is right, if you want to work in polar coordinates, what does this operator become? Well, you take one r derivative of your function, multiply by r, take another r derivative, and then divide by r, plus take two theta derivatives, divide by r squared, and then this z component is unaffected. Okay. And so in a very special case, right, so a priori, our function is going to depend on, right, our polar coordinates and z, right? But maybe we say, you know, it's radially symmetric, so it doesn't actually depend on theta. So now u is just a function of r, z, and t. What does this operator look like then? Well, if u doesn't depend on theta, right, take a theta derivative, right, du d theta is going to be 0. So this term is going to go to 0, and the Laplacian applied to u is going to look like this. Okay. So one question is, well, you know, why? Why does the Laplacian take this form? You know, where are all these terms coming from? Why are we multiplying and dividing by r, etc.? And kind of where all this comes from, that's going to be derivation, a derivation in some of the homework. But maybe the thing to take away here is that, right, if we change coordinates, we can still compute what this thing is in the new coordinate system. It just may look a bit different. Okay. But working with the Laplacian and polar coordinates is something that we'll use later in the course. Okay. Okay, so that's polar coordinates, right? You can do the same thing if instead you want to work in spherical coordinates, right? What does the Laplacian look like? So in spherical coordinates, right, x, y, and z, take those forms. The picture is the following. Right, so that's our x-axis, y-axis, z-axis. And then spherical coordinates will be, how do I draw this? So let's see. Take a point, say, out here. Okay. This is going to have some distance r associated to it. It's going to have some angle down from the z-axis. And this angle is going to be phi. And then kind of this point, if you kind of project down and look down, it's also going to have, so let me draw something like that. So it's also going to have some angle theta kind of in the xy plane. Okay, so these are spherical coordinates, right? Sometimes they're more convenient or better to use than polar or Euclidean coordinates. And then the question is, well, what does the Laplacian look like in that case? And so apply the Laplacian to a function u. Takeaway is that Laplacian takes this form. Okay, so we won't do anything with spherical coordinates, but the point is that, again, change the coordinate system, you can figure out what this thing looks like. And so then if you want to solve the heat equation, right, you essentially have du dt is equal to k times this thing, and you can write this thing out in terms of the coordinate system you care about. Okay. And that's it for this section.